Okay, in this chapter here, we started talking about obviously a little bit more into solutions, particularly. Remember, a solution is pretty much made up of basically two things. It's made up of that solute, which is the smaller part of the solution, and it's made up of the solvent, which is the larger part of the solution. And really, that is. What makes up a solution. And we talked about sort of the properties of solution and really more so sort of solubility of solutions, sort of solutions in solutions. And remember, when we mix solutions together, sometimes we refer to that as being miscible if they kind of mix and are soluble in each other and pretty much dissolve. We also have ones that are immiscible, which basically means when they kind of mix together, we do see different layers. So, um, what really sort of determines whether or not something will sort of mix, and especially dealing with solutions and really anything in particular, is it really has to do with those intermolecular forces that we talked about in the previous chapter. Remember that there's basically, three major types of sort of intermolecular forces. Those are, again, the forces that hold one particular molecule together with another. As we talked about, there's hydrogen bonding, which is a relatively strong intermolecular force, and that is a bond between hydrogen, that's between hydrogen, nitrogen, oxygen, or fluorine. And that sort of attraction is very, very strong. We have dipole, dipole, which is also sort of used for polar molecules. But again, they don't have the sort of the ability to hydrogen bond. So they kind of use those forces. And sort of the weakest out of all of them is our sort of dispersion forces. And if you remember, as we talked about, those are sort of those temporary forces that sort of hold molecules together. And in terms of sort of the types of compounds that kind of use those different intermolecular forces, really polar molecules use either a hydrogen bonding or dipole dipole. Again, those are sort of the major sort of intermolecular force that works with polar sort of compounds, while pretty much our non-polar guys are going to be strictly using dispersion forces, those really temporary forces, and again resulting from perhaps the electrons kind of deciding to go one way or the other, sort of making a temporary positive charge and negative charge in a nonpolar molecule, which normally does not have a charge at all. Or you can induce sort of a temporary charge, which is sort of what happens, when you do mix, something that's polar and nonpolar together, for a short period of time, they're able to sort of interact a little bit with each other. But really, over the long sort of haul or long period of time, they have no way to really maintain those sort of attractive forces between them. Sort of, I think maybe I used it before, but sort of like the oil and vinegar sort of salad dressing example, you can kind of really mix it for a short period of time. It does say relatively mixed, but if you put the bottle out, you could definitely start seeing it sort of separating out from each other. And again, over that long period of time, they don't have sort of a way to sort of maintain that connection. So what that has to do with sort of solubility and things being sort of able to mix with one another is we came across that idea of what you commonly hear a lot of, which is like dissolves like, which means basically things that share similar sort of intermolecular forces are able to be sort of soluble in each other because they have sort of a very similar way to interact with one another. Um, so if you just think about, for example, water, when we go and dissolve something there in water, we basically, before we do that, got a bunch of water molecules that are pretty much hydrogen bonded to each other. So, in order to get something to dissolve in it, we need to kind of break this bond between a water molecule and a water molecule and really replace it with something that's kind of similar, not giantly big or anything like that. And that's why when we, see something that, like I think we saw methanol, for example, which although it does have a non-polar part, does have this polar part where it could also do some hydrogen bonding here. And it's that interaction which allows something like methanol, for example, to be fairly soluble in water It's also not ginormously big, so it's able to kind of fit in with all the water molecules that are around, and it makes it relatively soluble. Now, if we take something like water and we try to mix it with sort of a really non-polar sort of guy, however many carbons you want, but we'll just draw a simple one here. Something like CH4. This guy is non-polar. Again, he's going to be using that dispersion forces. Water going to be using hydrogen bond. There's really no way for them to sort of interact because water is partially negative, partially positively charged, but there really is no sort of positive or negative sort of charge. So what happens is, for the short period of times, it can kind of gain a temporary charge, but it's not going to hold out for a long period of time. Those electrons or whatever are going to want to kind of come back. There's going to be no long way sort of way for those guys to interact. And that really is sort of the difference between, say, something that can do hydrogen bonding and something that can do dipole dipole, and something that's sort of nonpolar and can do dispersion forces. When we have a polar molecule or some aspect that's sort of polar on it, it means that basically that molecule, no matter what the situation is, always has that sort of positive negative charge available to do these type of interactions with. When we have something that's a nonpolar molecule, it really, under normal circumstances, has no charge. So it's depending on something to occur to give it that temporary charge. And that's why dispersion forces are so much weaker than polar or dipole, or hydrogen bonding, because when we're dealing with polar molecules or when we're dealing with things that are ions, they're pretty much good to go. They got those sort of charges no matter what the situation is. A nonpolar molecule is not like that. It needs something to sort of occur to allow it to interact well with something else. So that does bring up that idea, as we talked about, of like dissolves like. And essentially what that means is, again, things with similar sort of intermolecular forces will basically be soluble in each other. So the main list that sort of occurs on this is, if you take something that's ionic, it will be okay with something that's polar. Again, it will do that sort of ion dipole interaction. If you have something that's polar, it will definitely mix with something else that's polar, because they both will either be using hydrogen bonding or dipole dipole interaction. And the one that sometimes people overlook is, if you have something that's nonpolar, it will actually be soluble in something else that's nonpolar. Because in that situation, even though it's the weakest of those interactions, they both will be using the same type of interaction. So when you get two nonpolar guys together, they actually are going to be soluble in each other, because it's normally how they sort of interact with themselves through those dispersion forces. So they're able to, again, find a way to interact really well with one another. It's really only when you kind of get the polar and non-polar crossover that you really get things that are not very soluble in each other and really will not mix. Any questions on that stuff we sort of talked about the last time? Okay, so I think where we left off was about here, I hope. So this is, I think, where we left off, which is talking about sort of hydrophilic and hydrophobic. And hydrophilic basically means that it is something that is water loving, as it says. It basically means that it is something that can interact really well with water. It has similar types of interactions. And this could be a region that's polar on a particular molecule. So if you remember, we've seen a couple, for example, like ethanol, which looks something like this, which is an organic guy right here, ethyl alcohol. And really, when we look at something like ethanol, it really does have sort of two parts. It has a part that really is nonpolar, and that's really this part right here, highlighted in yellow. It's all those carbons and hydrogens and stuff like that. That's pretty much your nonpolar region of this particular molecule. Now, that would might make you think that this guy would not be available to sort of interact well with water, but it actually can. And it's because, although it has sort of that nonpolar region, It also has a polar region, which is obviously, as we probably talked about previously, right here, that OH group. And as we talked about before, that OH group is essentially the exact same OH group that we find in something like water. And that is sort of our polar region. That's our non-polar region of this guy. And because it is not such a big molecule or anything like that, that little region of ethanol allows it again to really interact well with water, allows it to do its hydrogen bonding thing. And again, it's fairly soluble in water because of that. Um, I think I might have talked about before, but if you do sort of get this non-polar region becoming too large, usually in organic compounds like these guys, 6 or more carbons, kind of involved on that side, um, you do definitely decrease the solubility a lot. So you decrease that solubility a ton by doing that, kind of building out. Really, two things ends up happening when you kind of build out a very long sort of carbon part, carbon hydrogen part, that kind of yellow part that's non-polar. When that gets really big, what you end up doing is you have a very big part of the molecule that's non-polar. Not to mention the fact that the molecule itself has now got very, very big, which means it makes it really hard to kind of get in there with water, which is a relatively small molecule. It's kind of like parking, a semi truck in the garage. You could get some of it in maybe, but not the entire thing. It's not going to fit perfectly right. As opposed to if you had a really small, like smart car, it would fit in there with no problem. So it's sort of a similar idea. It gets what's sometimes referred to, as I might have mentioned earlier, as well as sometimes referred to as steric hindrance. It just kind of gets in the way. So even though it still has this OH group, it really is not very productive because it has this big sort of group that's sort of blocking its ability to interact well with water. Also, as well, there are certain things that are larger molecules that are still relatively soluble in water, and that's because they contain a lot of like OH groups. So the opposite of that is if you have some type of molecule where it actually is kind of littered with a bunch of OH groups on there, that definitely increases the solubility with water. I think we'll see this a little bit later on here in this chapter, but something like sugar, for example, sugar is a little bit larger of a molecule, but it is pretty much littered with OH groups all over it, which makes it fairly, fairly soluble in water because everywhere there's an OH group, it allows it a place to interact well with water. Hydrophobic, on the other hand, is basically a water hating. It doesn't like water. The nonpolar hydrocarbon region of ethanol, which is the yellow part here, by the way, is that hydrophobic part. So if we look at ethanol, which is what I drew up here, the green part here would be hydrophilic. I'll just put green. And the yellow part up here would be the hydrophobic region, the part that doesn't really like water. That's actually kind of what soap does. Soap pretty much is something very similar to this. Soap is really this super long chain of like a fatty acid sort of thing, but basically this really, really long chain of hydrogens and carbons. And it definitely has this sort of, and it just kind of keeps going. It has this hydrophobic region, which is obviously here where I'm drawing all these carbons and hydrogens. Kind of wish I didn't draw so many carbons there. And it also will have this polar part, which is sometimes referred to as the polar head. And this has what is sometimes referred to as a carboxylic acid type group. This is the polar region of soap. And this is the obviously non-polar region of something like soap. And this works really well in terms of sort of solubility as what we've been talking about. Because this is a non-polar region, that is pretty much the part of soap that will, pretty much hook up with dirt. Dirt, for the most part, is non-polar. So when you put soap on, it pretty much kind of surrounds and mixes well with the dirt part. I'll just put like a circle around it. And what that ends up doing is actually trapping the dirt. A whole bunch of soap molecules, by the way, come around and trap the dirt there in the middle. And what that ends up doing is when all these soap molecules basically come around and trap the dirt, what's sometimes referred to as a micelle, it leaves this polar region of soap sort of exposed at the surface, all the way around sort of the dirt, if you will. And that's really good because typically when we put soap on, as we talked about the other day, I think as well, we throw some water on that, which is polar, and the polar water and the polar part of soap, which now has your dirt trapped, is going to mix really well. And when you wash off the soap, because it will be soluble in water, because all the polar parts on the outside, it will also take obviously the dirt with it as it basically goes out. Soap is a very good example of something that has, sort of a non-polar region, which again, not very soluble in water. It's very hydrophobic, but very soluble in dirt, which is also non-polar. And it also has a hydrophilic region, which is sort of the charged part of it up there where the carboxylic acid group is. That's the thing in the box on the right. And that's the part that really likes water, so it works really well when you mix them together. Any questions on that there? Oops. So here's an example of a couple of things, and just to look at these things, this is octane and carbon tetrachloride. Octane is, much like the name might sound to you, it is 8 carbons. And I won't draw all the hydrogens, but pretty much hydrogens all the way around the thing. And as you can see, since it's a big chain of carbons and hydrogens, it is going to be non-polar. And that works really well. As you can see, when you mix it, it all looks like it's mixing, and it is mixing. And that's because it's not mixing with water, but it is mixing with carbon tetrachloride, which I think we might have also looked at maybe the other day. But if we look at carbon tetrachloride, again, geometry wise, this again is 4 electron pairs, 4 bonds. That is tetrahedral. That is symmetrical. That is everything attached on the outside the same. That means that this guy is also nonpolar. So as we mix these two things, again, they're going to be using both really dispersion forces, and they're going to be able to interact with each other over the long period of time, because that's essentially how octane and octane interacts with itself, and essentially how carbon tetrachloride and carbon tetrachloride interact with each other. So when you mix the two, the interactions that they are seeing is essentially the same interactions that they have with themselves, and that makes it very, very soluble. And that's very different if we then dump gasoline, which is an even longer chain of carbons and hydrogens, like I drew up there, with water, as we talked about before. Again, typically what you'll see is this separation that's going to occur, and we see some distinct layering that's happening here. And again, that's because, as we mentioned before, this guy also going to be using the dispersion forces. Here are hydrogen bonding going to happen here. And this is definitely not two things that have similar intermolecular forces. So they will not be able to maintain any type of significant interaction for a long period of time. In reality, as I might have mentioned when we were talking about sort of intermolecular forces, pretty much anything for the most part can do a little bit of dispersion forces. So even something like water could use some dispersion forces for a bit. Anything that's polar could use some dispersion forces. But it's really not the main sort of force that it uses to interact with other molecules. And that's why, again, we do get sometimes kind of that temporary sort of interaction that occurs between things, again, like that salad dressing sort of example. You get that temporary sort of interaction, but eventually what happens is they can't maintain it, so they do sort of separate out uh, into some different layers here. So let's talk a little bit more about solubility, and a little bit more about sort of making solutions. When we have one substance, which is usually the solute, and again, the solute is the smaller part of a solution. It's usually the thing that you dissolve, and you dissolve it in the larger part of the solution, which is the solvent. By the way, the name of the solution, as we might have mentioned as well, is what the solute is. So again, if you have a sodium chloride solution, that's pretty much the solute, is the sodium chloride. And they're said to be soluble. So salt, like sodium chloride, for example, is soluble in water. They're soluble in water really because of those ion dipole interactions, right? When you put a ionic compound in water, it's going to be attracted to the negative side of water in the case of the positive guy. and the positive side of water in the case of the negative ion. Those guys, again, is what happens, as we might have mentioned as well, that it really doesn't go anywhere, this stuff. It just sort of disappears into the water network, because there's not just one water obviously surrounding these guys. It gets surrounded by a bunch of them. How do we help it dissolve? Well, we usually, when we put some type of solid in water, we oftentimes will stir it, right? So when we stir it, we do two things. We're adding a lot more energy as we're stirring, and we're also basically just throwing a bunch of water molecules all over that salt. And everywhere the water molecule basically comes into contact with that salt, it's going to really initiate the dissolving process to occur. And that's why, right, when you dissolve something, you stir it a lot of times and it goes away a lot faster than if you just kind of dumped it in there and waited for it to naturally sort of move around and dissolve. So that sort of stirring action, more energy, putting more water molecules all over the salt, allowing it to really dissolve a lot quicker. When we have one substance that really doesn't dissolve in another, it's again said to be insoluble. Oil is insoluble in water. And again, a lot of times when we talked about sort of miscibility and immiscibility and soluble and insoluble, typically miscible and immiscible, like we talked about at the beginning, is usually sort of terms that are used when we're talking about sort of a liquid and liquid sort of mixing, or a solution and solution mixing. When we talk a lot of times about a solid and a liquid sort of mixing, that's a lot of times when we refer to it as being soluble or insoluble. So that's sort of the little distinction there between those two sort of terms. There is a limit to the solubility of one substance in another. Gases are always soluble in one another. And if you just think about gases and what's happening with gases, they are obviously flying around, which means just by that process, if there's another gas flying around, they are constantly mixing with one another. So they are typically soluble in each other. Some liquids are also mutually soluble in each other, so that like dissolves like. So polar and polar guys are good, non-polar and non-polar guys are good. Obviously, as we talked about, polar and non-polar, not so good, not really going to mix very well. Molecules, again, as we talked about, that have similar structure means that they probably have similar sort of intermolecular forces and abilities. And that brings up that idea again of that like dissolves like. When we talk about the solubility of a solute and a solvent, it does depend on temperature. Typically, when we have a higher temperature, we could get a larger solubility of a solid dissolving in a liquid. Maybe you have experience in this, and maybe in a lab or just in general. If you have something that's sort of not dissolving, very often people will recommend, hey, why don't you just kind of warm it up a little bit or heat it up a little bit. And actually, solubility is, in terms of like a solid in a water or something like that, or a liquid like that, is really tied to temperature. Uh, at a particular temperature, for example, at 25 degrees Celsius, for example, there's only a certain amount of, say, sodium chloride that you could get to dissolve in 100 grams of water. If you increase the temperature, that amount of sodium chloride that you could dissolve in the same amount of water will actually increase, and vice versa. Obviously, if you lower the temperature, you will see a little decrease in the solubility of that solid. So there is a limit at a particular temperature. Even something that will dissolve, at room temperature, for example, there is a limit to how much that you could get to dissolve in an amount of solvent that you have. Again, just a common example of that is, if you take some of those sugar packets, for example, you could get those to dissolve right in like a cup of water. If you got like the Costco size thing of sugar and you dump it all into that same cup of water, at some point, all that sugar is not going to dissolve, right? It's going to pile up on the bottom, and obviously you will not get it to dissolve. So there is a limit to anything in terms of its solubility, and a lot of it is dependent a lot of times on temperature as to how much you could get there. When we have a lower temperature, we have a larger solubility of a gas in a liquid. That is because when we have a gas in a liquid and we lower the temperature, that means that this gas molecule is now going to be moving a lot slower, which means he's going to find himself in that liquid part, dramatic drawing here, for a much longer period of time, which means that the gas and the liquid are going to be mixed together, rather than if we had obviously a much higher temperature that gas molecule would gain a lot of energy, right? And maybe shoot out of the liquid part because it has a lot more energy associated with it. In addition, when we talk about gases, the solubility does depend on pressure. The higher the pressure, the larger the solubility of a gas. So we'll see it here in just a second as well. But the common sort of example of that is like a soda can, right? In your soda can, you have a lot of water, syrup, and some other stuff, I guess, depending on the soda. And you also have a lot of CO2 molecules. And obviously, before you pop the top there, this is under a lot of pressure, which is going to keep basically your CO2 dissolved in the liquid part, which is good because, that keeps your soda fresh and not so sort of stale in that case. Now, what happens when we kind of pop the top, right? When we pop the top, two things happen. You sometimes will see some fizz coming out, right? And that's like the CO2 that now has an escape route. You also lessen the pressure, which means that CO2 is going to come out of the liquid and also out of that escape route. Also, why when you leave a soda can open for a while, you come back and drink it and go, I should not have done that perhaps. It doesn't taste so fresh anymore because A, you alleviated the pressure, allowing the gas molecules to escape the liquid part easier, and you also provided a nice escape route for those guys to escape. There you go, real life examples. I like it. All right, any questions on that there? So, here in this picture again, this is sort of the hydration process that occurs. It's maybe hard to see. It's kind of hard to see on my side, but this guy's stirring, I think, some sodium chloride in here with some water. And really, as we stir, what we're doing is you can see these kind of red and white guys here. They're all water molecules, and they're just basically being flung on this ionic solid. This would be your salt part. Remember, the salts arranged in that very ordered crystal solid lattice that we talked about when we're talking about unit cells. And again, by doing a lot more energy, a lot more water molecules, and basically they come in the water molecules as they're floating around and kind of pluck off the ions. And when they do, as you can kind of see here, positive ion gets surrounded by the oxygen of water. The negative ion gets surrounded by the white circles there, which represent the hydrogen in this case. And again, that's basically the dissolving process. As we talked about before, again, it's really not going anywhere. It didn't disappear. And that's why when we dissolve something, it is just a physical change. It's not a chemical change. Nothing has reacted. It's still there in its original form. And as we mentioned, I think previously, and maybe a number of times, if you start heating that sort of salt water, the water molecules will evaporate off. And again, that will allow the positive ion and negative ion to basically come back together, and you would get your salt back. And again, that's why it's, again, a physical change when we do some type of dissolving rather than a chemical change. As I mentioned before, there is sort of that limit to how much that you could get to dissolve in a given amount of solvent. And it is a lot of times temperature dependent on it. So if we have a situation where we've added maybe too much solute to the solvent, we get what is sometimes referred to as a saturated solution. And a saturated solution is pretty much that point where we pretty much have hit the maximum amount of solute that will dissolve in that solution. So if we hit that saturation point, it's sometimes referred to, we pretty much hit the maximum amount of solute that will dissolve at a given temperature. So what does that mean? It means realistically, if you were doing this in a lab, you probably would see solid at this point. But technically speaking, it's almost the saturation point, or when you hit that saturated solution, it's almost like the tipping point where you kind of won't see solid. But if you decide to try to dissolve any more at that point, you're at that tipping point where it's not going to dissolve anymore. And you would expect to kind of see a solid at that point. So sometimes people think about it as saturated solution as one where, we do see solid. And it's technically the point where the max amount has dissolved at that point. And again, if you take it like a crystal or two over that point, those crystals are not going to dissolve. And that's why I say in lab, we sometimes will sort of see solid in the solution at that point when it's a saturated solution. And that's because if we're making it, for example, in the laboratory, the only way we could kind of visually see that we've hit a saturated solution is to keep dumping the solid in until no more dissolves and we still have solid that's there. And that's why we sometimes would say, we kind of see a solid at that point. But I guess technically speaking, it is really sort of that tipping point to where you would see a solid start to form or that guys would not dissolve. The opposite is true if we kind of hit the point where we dissolve some solute and it continues to dissolve. That is what is referred to as an unsaturated solution. So unsaturated means we haven't hit that point yet. We can continue to dissolve the solute and it will continue to dissolve. It will continue to dissolve until you really hit that saturation point, or you hit what is basically a saturated solution. So an unsaturated solution really isn't at that point yet. For example, we go back to sort of the sugar example. If you dump in a couple of packets of sugar into like a cup of water, it probably will dissolve. You're probably still in an unsaturated solution. Maybe dump a couple more in there. Maybe it dissolves. You're waiting a long time for your food, so you dump every single sugar packet that's on the table in there, and then grab the bottle of sugar and start dumping it in, and you start mixing it, and it stops dissolving at some point. That's pretty much the point where you hit the saturation point and a saturated solution, and obviously no more will dissolve unless you do something to it, either add more solvent, heat it up, or something like that. And another sort of type of solution is one that is referred to as a supersaturated solution. A supersaturated solution is essentially a solution that contains too much solute dissolved in the solution. It's kind of like an unstable solution if you want to think about it. So, how do you make sort of a supersaturated solution? A lot of times we'll use like sodium acetate or something like that that comes from acetic acid or vinegar. So typically what you would do, one way you could do it is you could actually just make a saturated solution. So if you make this sort of saturated solution, you now have in here dissolved as much of that solid that you could dissolve at that given temperature. So what can you do? You can then heat it up a little bit. When you heat it up, you can even add a little bit more solid or even have more solid than you should to begin with. As you heat it up, one of two things is going to happen. It's going to increase the solubility of that solid in that liquid, which means it's going to remain dissolved. In addition, as we heat it up, we're also kind of removing some of the water molecules, right? Because some of the water molecule is going to basically dissolve. And what we typically do sometimes in this sort of experiment, which is a common experiment that's sometimes done at schools, is you make this sort of supersaturated solution by putting way too much of that solid in there. You then sort of heat it up a little bit, making sure it all dissolves. You then very carefully let it cool down. You let it cool down. So now what we're doing, if you remember, the solubility of stuff is basically based on temperature. So as we were heating it, we're definitely increasing the solubility of that solid. And we got all this solid now dissolved in there. And it'll look like a solution, like nothing's floating around, nothing's in there. But now when we let it cool down, we're bringing it back down to a temperature where we should only have less amount of that solid dissolved. So at this point, it will look like a solution. And, we cooled it back down. The solubility of all that stuff that's dissolved in there is now a lot less than what we actually have dissolved in there. We have kind of like an unstable solution at this point. It looks like a solution. It's got just way too much solid basically dissolved in there. It is so unstable that, during this type of experiment, one of two things could happen if you're not really careful with this thing. You could actually just knock it by accident or tap it. And by tapping it or knocking it, that would be enough for all the solid that's in the solution to basically decide, no, I don't want to be here anymore. All the solid will essentially come out of solution and it will go from a solution to like a rock hard solid at that point. all literally from just accidentally maybe tapping it too hard, placing the thing down on the bench too hard. What most often we do in these experiments is we kind of trigger that by taking, believe it or not, like the smallest little speck of the solid that's dissolved in there. And you just kind of dump that one little seed crystal, is sometimes called, into there. And that one little speck of a solid is enough to tip this guy over the limit and go, no, you guys should not be in here. It's kind of a cool thing. Is a lot of times you'll see it start like solid coming from the middle and kind of working out. And before you know it, this entire thing becomes like a solid, rock hard solid at that point, no longer a liquid. So basically, a supersaturated solution is one where we sort of get too much, way too much of that solid dissolved in the liquid part. Usually is sort of an unsaturated solution. I'm sorry, usually is an unstable solution, and it doesn't really want to keep all that solid dissolved, and it doesn't take a lot for it to go, I'm done, I'm going to get rid of all the solid, and all the solid basically will come out. Any questions on that there? And here's just a graph for sort of solubility of ammonium chloride in 100 grams of sort of water. And you can see, depending on sort of the temperature, as the temperature increases, we'll just look at this, say at 10 degrees Celsius, for example, we could get, about that much, sort of 20 grams or so. We come out this way, coming up, we could get it all the way to dissolve, all the way up outwards in terms of amount that will dissolve. So as the temperature increases, you can see you can get a lot more to dissolve, as opposed to actually, you probably go up this way, actually, in terms of dissolving. But you can get a lot less, obviously, as you lower the temperature. So temperature does play an important role. And this is actually the step-by-step picture of what I was just talking about. This is a supersaturated solution of sodium acetate. You can maybe barely make it out, but like he just did like one super small speck of that sodium acetate that was dissolved in there. And you could kind of see as soon as it kind of hits into there, it starts to, this is all the solid coming out of the solution. You can see at the beginning it was a solution. That one little speck of something that he just dropped in there that you can barely see is starting to cause all of that solid to continuously come out of solution until eventually this entire flask will now be pretty much like an ice cube. It's not really ice, but it'll be rock hard solid at that point. And again, that's really how unstable sort of a supersaturated solution is, because you pretty much created a situation where you definitely should not have that much dissolved in there, and it realizes it at some point and it's not able to maintain that. So let's talk then a little bit about the pressure on the solubility of gases. So we kind of got there a little bit earlier a second ago, but this is sort of our classic soda can example here. The external pressure has an effect on the solubility of gases, and that relationship is what is sometimes referred to as Henry's law. Henry's law states that basically the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. And we get here, which is a version of Henry's law. Sometimes people use some different sort of symbols, like molarity instead of C. But C is the concentration, which is basically the molarity, which is our moles per liter. P is the pressure in atmospheres. And K is a constant, and it is Henry's law is constant. So this is Henry's law constant. And it is specific for the gas. So it is specific for a gas. So for example, if we were talking about our sort of soda can like earlier, we would be talking about the gas being CO2 being dissolved in there. And this is where you can sort of calculate things like, what concentration of that guy should you have to keep it at a certain pressure, or what pressure do you need to keep the concentration of a gas at a particular pressure, which would be important. For example, in that soda can example, you may need to keep the pressure of your soda can at a specific pressure to allow the right amount of concentration of CO2 gas, for example, to be dissolved in the liquid part so that when you pop the top, you do have a pretty fresh can of soda. It's not sort of flat from the get-go and stuff like that. Here is a table, which obviously, if you had to do any type of calculation, would be provided for you. And again, you can see it is specific, and you get sort of a different Henry's law constant here, depending on sort of the gas. You can see the units here are molarity divided by atmospheres. Here's a prettier picture probably than what I drew my soda can, but kind of the same idea. Again, before the top is popped, very much high pressure. You can see a lot of the gas molecules really dissolved in the liquid part. And as we talked about, once you pop the top there, you again are basically allowing those gas molecules to be less soluble in the liquid part. And as we talked about before, hence the whole flat soda aspect of it, you're also allowing an escape route for that CO2 molecules basically to escape, which means when you get your carbonated soda, it no longer feels carbonated very much because, it all escaped out the top. Any questions on that there? So as I mentioned before, you can do some type of calculation here using Henry's law to figure out certain things. So for example, here, if we wanted to figure out the pressure of CO2 that's required to keep the carbon dioxide concentration at 0.12 molar in soda at 25 degrees Celsius, we could use Henry's law, which is what we saw a second ago, which is our concentration is equal to our KH times our pressure. Sometimes people will also use, like I said, S for solubility, which is kind of the same thing. Molar solubility is basically what the S stands for. We would obviously, in this case, because we're dealing with CO2, we would want to go back to our table and grab the Henry's law constant for CO2 off of that table. And if we did that, we see that the K here is 3.4 times 10 to the minus 2 molar over atmospheres. So we really can solve for pressure here. So pressure would equal our concentration divided by our Henry's law. Concentration that we're looking to keep it at is 0.12 molar. Our constant for CO2 specifically is 3.4 times 10 to the minus 2 molars divided by atmospheres. When we do that calculation there, we end up with, looks like 3.5. The units here will be atmospheres, as the molarity and the molarity will cancel. When you do the division, the atmospheres come to the top here, which I hope is what they have here, I suppose. Any questions on that? So if you think about your can of soda in this example here, that can of soda before you pop it has a pressure of about 3.5 atmospheres. If you remember from our conversation about gases, that normal sort of pressure we deal with is about 1 atmosphere. So we have to keep it almost 3.5 times that of sort of normal pressure to keep that CO2 sort of dissolved in that concentration in a soda can. And again, that's why it's under pretty good pressure there. Any questions on that there? Okay, so we're going to talk about some concentration units, and again, some of which I think we maybe have covered before. So we'll kind of go through some just to make sure everybody again is on sort of the same page. We talked about some percent units, if you remember. And again, just to make sure on this one, this is the percent mass to mass. And that's our mass of our solute, as it says there, divided by the mass of the solution times 100%. And remember, the key of this one is the bottom part here. You want to make sure that you get both the solute and the solvent there when you're doing that. We also saw a couple of other sort of percent concentrations, percent volume to volume, which is the volume of a solute divided by the volume of solution times 100%. And we also saw percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. So remember, you could kind of plug and chug into these. You could also, if you had, a 3.7% mass to mass sodium chloride solution, you could kind of turn this into a conversion factor by assuming 100 grams. And that would mean that you had 3.7 grams of sodium chloride and 100 grams of solution. You obviously could flip it around and use it as a conversion factor the other way. It would work the same way with volume, and mass to volume. Any questions on that one? I think we covered it when we started talking about molarity in that area, I think. So again, if we go through this and we wanted to, we prepared a solution by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the mass percent? The 2.5 is the smaller number, which means this guy is going to be our solute. The water here is the larger number, which means it's going to be our solvent, which means when we calculate our percent mass to mass, the mass of the solute divided by the mass of the solution times 100%. Our solute is 2.5, so it would be 2.5 grams. But remember, it's not just the 50 here. That is the solvent. We do need to add it to our solute for the bottom. So we would take 50 plus 2.5 grams. Again, that's going to get us the mass of the entire solution, not just the solvent, which is a very common mistake, as we talked about, that people sometimes will make. And that will get us 4.76% by mass. Whatever this is, calcium chloride. Any questions on that one there? All right. We also, again, looking at this example, we can treat this, like a conversion factor. We're looking for the mass of the hydrochloric acid that would be in this solution. That's 37.2% by mass. So we really can convert that into a conversion factor, which means there's 37.2 grams of HCl and 100 grams of solution. Or again, if you need it the opposite way, you can flip it around. What is the mass of HCl contained in basically 35.5 grams of solution? We know that's the solution because we're looking for the HCl. The name of the solution is HCl, which means that this is our solute in this case. So we can, again, kind of do it conversion factor way, taking 35.5 grams of solution, using our conversion factor on the left there, 100 grams of solution is 37.2 grams of HCl. Grams of solution will cancel each other out. We will end up with 35.5 times 37.2 divided by 100 gets us 13.2 grams of HCl. And again, this sort of conversion factor way, as we've talked about before, is really the same thing if you just plugged and chugged into the formula. It actually is pretty much the same calculation, because this would be obviously 37.2%. The mass of the solute is what you're looking for. The mass of the solution was 35.5 grams, and times 100%. Again, to solve this, we would multiply this to the other side, which is essentially what we just did here. And we would divide by 100, which is essentially what we just did here. So again, you could put it into the formula if you want, or you can, kind of do a more conversion factor way. Question on those kind of percent by mass sort of guys. Now, another sort of concentration unit, which I don't think we've talked about yet, is this guy here. And this is actually molality. So this is molality, not to be confused with molarity. So they actually use kind of the same symbols. This is actually lowercase m, which also means that we are not talking about mass here. It is actually molality. So little m, which is molality, is the moles of solute divided by the kilograms of solvent. So moles of solute divided by the kilograms of solvent, not to be confused, and for exaggeration purposes, big M, which is moles of solute over liters of solution, right? Or moles per liter. So big M is molarity, little m is molality. Kind of works the same way. You know, if you had something that is 4.5 molal or molality, sodium chloride, what that would mean is you can convert this little m into usable units, much like we talked about when you have molarity. It's always a good idea to convert that big M into these units so that you can see both of those units. Here with molality, that would be 4.5 moles of sodium chloride in a kilogram of solvent. So again, kind of turning that little m into both of these units can oftentimes be very helpful, especially when you're doing calculations so that you can actually see what units are canceling, what units maybe are not canceling. Again, sometimes much like molarity, when people leave the big M in, they oftentimes will forget where like liters is or where the volume went and stuff like that. And same thing happens here. Sometimes when people leave it as like the little m, sometimes people get confused as to, kilograms is where or moles or forget all about the kilograms part. So sometimes usually good idea to kind of convert it into these sort of usable units. Any questions on that there? You might be wondering what might tie these two together. What ties these two together is actually density. Grams per milliliter of solution, grams of solute really per milliliters of solution. That's sort of what ties these guys together. If you ever have to go, kind of from molarity to molality, oftentimes density of the solution there is sort of what kind of ties those guys together and allows you to kind of go from one to the next. So why don't you try one here? So take a second and why don't you calculate the molality of a solution prepared by dissolving 61.7 grams of propanol there in 175 milliliters of water. The density of water is 1 gram per milliliter. So take a moment or two and see what you come up with. Not molarity, but molality. And molality being the little m is our moles of solute divided by kilograms actually of solvent. So not a volume on the bottom or anything like that, but actually like a mass on the bottom. So in this particular case, we want to calculate the molality of it. We need the moles of the solute. Obviously, we're dissolving this guy in the solution, not the end part. We'll go that way. So that is going to be our solute. The water here would be our solvent in this particular case. And this guy obviously here would be our solute. So we have the grams of our solute, so we do need to get it into moles. So we would take our 61.7 grams. Now that I scribbled all over it, I think it is C3H7OH. We need to convert it into moles, so we would go to the periodic table, which I hope we know at this point. So that is 3 times 12.01 for the carbons, plus 7 times 1.008 for the hydrogens, or at least 7 of them, and 16 for the oxygen, plus I missed the one hydrogen there at the end, so we'll add it in. And that looks like we get 60.09 grams per mole, which would be the molar mass from the periodic table. Grams going to go on the bottom, so everything cancels out okay. So grams and grams. And we take 61.7 divided by 60.09, yielding us like, we'll go with we'll round it a little bit, 1.03 moles of this guy. Any questions on that so far? That essentially is the top part of what we need there. So we need now the bottom part, which is kilograms of solvent. We know our waters are solvent. We know we have 175 milliliters of water, which is our solvent. Remember that in the case of molality, we're not looking for volume, but we're actually looking for mass. And that is why the density of water is given to you, because we could use the density of water and the volume of water that we have there to convert it into mass, right? Because that's grams per milliliter. So the milliliters will cancel. I think I could do this math. That's 175 grams of water. We have now, using the density of water, converted our milliliters into mass, which is grams. But again, we don't want grams. We actually want kilograms. So again, we have one more conversion we got to do here. We got to take it from grams to kilograms. And there are about 1,000 grams in 1 kilogram. That's going to give us 0.175 kilograms basically of water. That is a long way to go here with my arrow. That is the bottom part of what we need to calculate the molality. Any questions on that part? At this point, we obviously have both parts to what we need. So the molality would be our moles divided by our kilograms, 175. And if we do that, 0.175, we get something like, we'll call it 5.87. Now, you might be wondering, in terms of units, what would we leave it as? And by the way, you might get 5.88 if you use the 1.03. It's okay. You can leave it as moles per kilogram because the units did not cancel out. You could also, very much kind of like what we do with molarity, write 5.87 and little n. So again, those are kind of the two options in terms of what we do with those units. Any questions on that there? So molality, it's important concentration unit, especially for what we're going to talk about for the rest of this chapter. When we start talking about colligative properties, we use molality a lot in those things. So again, a reminder, moles per kilogram, and not to be confused, which is sometimes is with molarity, which is moles per liter. Another sort of unit that we obviously did talk about when we talked about gases and stuff like that and partial pressures, and that is mole fraction, right? And mole fraction is that X. And basically what that means is you would take the moles of A divided by the total moles in a mixture. The only difference is here we don't multiply by 100, right? So it's basically like a percentage without that whole percentage part of it, right? Where we multiply by 100. So we end up getting like a point something number, or, 0.5, 0.8, point something like that. And again, it's basically the moles of the guy you're interested in divided by the total moles. Obviously, if you had multiple guys in there, you would then perhaps do the moles of B divided by the total moles. Obviously, when you add up all the moles of what's present, it should add up to 1, because 1 basically means 100% is basically what it means. So in this case, let's take a look at one just to remind us. We want to calculate the mole fraction of methyl alcohol in this mixture. So remember, the first thing you kind of want to do is figure out the total moles you got going on there. So we have methanol and ethanol. We would simply add those guys together to get our total moles. And in this particular case, I think it's 1.257 perhaps. And since we're interested in the mole fraction of methyl alcohol, it is 0.328 moles divided by 1.257 moles would be the mole fraction of our methanol. And at this point, we would end up 0.328 divided by 1.257 would get us a what we got there, 0.261 as the mole fraction. And again, in this case, because there's only ethanol and methanol present, you could actually do the same thing for ethanol and calculate it that way by taking 0.929 moles, 1.257, going to get us 0.929 divided by 1.257, 0.7739. You also could get that by just at that point subtracting 1 would get you there. Again, because 1 basically represents 100%, and you could get yourself there as well. So again, we did see obviously mole fraction when we talked about partial pressures, and it's the same sort of mole fraction as before. Any questions on that one there? All right, so they agree, so that's good. This one I hope we know, which is molarity, right? And molarity is, again, a reminder, moles per liter. It really is moles of solute per liter of solution. We've talked about a number of times rearranging this, and obviously you can. If you want liters, that's going to be moles divided by molarity. If you want moles, which is a very common thing we do, which is liters times molarity. Um, Remember as well, though, if you decide to take milliliters times molarity, you are not getting moles out of that. You are getting millimoles, right? Um, which, it's okay if you decide to then divide by milliliters, because then you'll be back to moles per liter or molarity. But, if you're just going to do a standalone sort of calculation there, and you take milliliters times that molarity, remember, you don't actually get moles, but you're actually getting something that's referred to as millimoles. This is why when we did something like the dilution equation, we talked about the idea that you don't necessarily have to convert the volume when you use this equation into liters, because if you did milliliters here and milliliters here, when you multiply, say, M1 times V1, you would end up with millimoles on the left, and you divided that V2 to the other side, which would be milliliters. The milli part of it cancels, and you're back to molarity, which is what you would be solving for. So outside of sort of using the dilution equation, you definitely can, outside of using the dilution equation, you should definitely convert it into liters, as we've talked about, to make sure, obviously, that you are in the proper units. So, what we're going to talk about now that we sort of review some of these concentration units, and more importantly, talked about sort of molality, and we do see mole fraction kind of popping up in there as well, is we're going to talk about some properties of solutions which are known as colligative properties. And colligative properties basically means that the properties are sort of dependent on how many particles you have basically floating around in that solution. So what do we mean by that? Well, what we mean by that is in comparison to, say, a solvent by itself. So remember that a solution is, again, two things. It is the solute and the solvent together, right? And that's what really gets that aqueous sort of symbol next to it. When we have a pure liquid, like a solvent, that is sort of what gets like the else sort of symbol next to it, right? So if we take something like water just by itself, I'm not sure why our water is red, but we'll just go with it. So water by itself basically has a series of a lot of basically water molecules that are pretty much hydrogen bonded to each other, right? So if we decided, hey, we're going to heat this guy up and start to actually sort of heat the water up in the pure solvent, right? Kind of the pure solvent here. When we do, we'll reach a certain amount of temperature. And as we talked about, what will essentially happen when you sort of start heating it, you're adding energy, is going to break these intermolecular forces, right? And when it breaks these intermolecular forces between different water molecules, water molecule number one will decide I have enough energy. I'm now steam. I'm inside a bubble. I'm going to escape. Same thing with this guy, right? He's going to escape. Not going to be such an issue, right? It's going to perhaps boil at 100 degrees Celsius like we normally would sort of expect to occur. Also, if we had a beaker of, just sort of pure water in there floating around, and we decided to, I'm not sure how to draw this. I'm just going to go, hey, put it on ice. How's that? We put it like in the freezer or something like that, right? When we do that, what's going to happen is obviously we're removing a lot of energy, right? It's an exothermic process. Heat and energy is basically, going away. What ends up happening is, again, these water molecules will decide we're going to get a little closer, right? Everybody's going to slow down. We're going to start to form ice, right? With all that big empty space between the ice molecules. And we'll start to form basically ice in here in the pure sort of solvent. Now, when we have this pure solvent by itself, it obviously has nothing dissolved in it, which means that, there's really no sort of colligative properties. There's nothing there that's going to be problematic. Now, let's say we take the same water and we decide, we're going to put our water molecules in there. But sort of in addition to our water molecules, we're going to throw in there some other stuff, maybe we'll throw in some sodium chloride, some salt, because, I got some salt laying around. Why not? Throw some salt in there. It's going to throw in some sodium ions floating around, some chloride ions floating around, and then there. So we put all this sort of salt in there and sort of make a solution, for example, right? We now have some solute in there. We have a lot more particles sort of dissolved in this solution. Now, when I go to heat this guy up, what's going to happen is a couple of things, but as I start heating it up, my water molecules are going to break, right? But now you can just kind of see, even in my picture, this water molecule that just broke apart doesn't really have a clear path to escape, right? It's got all this other junk in the way, right? It's got to kind of work its way around and stuff like that to try to escape. If you got a water molecule down here with all this salt, there's a lot more junk in the way, if you will, right? So what's going to happen is it's going to take a lot more energy to heat this thing up to get these water molecules to kind of weave their way through all this salt and particles that are basically floating in that. What is that going to do to, say, the boiling point between the pure solvent and the boiling point in the solution? Well, we would expect the boiling point to increase. So maybe instead of this guy boiling at 100 degrees Celsius, it decides it's going to boil at 103 degrees Celsius or 105 degrees Celsius, because there's all these particles in the way of sort of the natural process of that solvent basically going to boil and going into the gas phase. Any questions on that? Kind of the same thing happens as well, as we'll talk about and kind of see as well. In the freezing aspect of it as well, you got all this water guys here, right? And they're sort of floating around, sort of interacting with each other. But again, if we just kind of put in there, some salt, which is sort of common, for example, maybe like rock salt, right? Making some homemade ice cream or something like that, right? You get all this guys in here. Again, in order for these water molecules to kind of get to each other, they got all this other stuff in the way. which means, we really got to remove a lot more energy here to allow them enough room to kind of get around and move some things out of the way. And again, instead of maybe freezing at 0 degrees Celsius where it normally would, the freezing point actually goes lower. Maybe it actually freezes at like, -5 or -10 or something like that, depending, I guess, on how much you put in there. Any questions sort of on that? So let's talk about some of the effects of having these sort of particles and stuff floating around in a solution versus maybe the pure solvent. One such process where we see an effect on it is what's known as vapor pressure lowering. So much as the name implies, we actually get the vapor pressure to kind of come down in the sort of solution versus the pure solvent. Remember that vapor pressure is really the pressure of a gas over a liquid, right? So the more gas molecules you have kind of floating over that liquid or flying around over that liquid, the more pressure you would have, the more vapor pressure you would have. So the vapor pressure of a substance depends on the nature of the substance and temperature. If we add solute to a substance, the vapor pressure is lowered because basically what we were just talking about, with all those additional stuff floating around in that solution, how do we get vapor basically to occur? We need to get things to kind of escape the liquid phase and kind of go into the boiling point sort of area, right? To go into the gas phase. So by putting all those solutes in the way, again, it really inhibits the ability of those guys to sort of naturally as well just sort of escape into the gas phase. Remember, at the surface of a liquid, as we talked about, you have sort of that process happening. You have guys that are sort of escaping the liquid part. You have guys that are dropping back down into the liquid part from the gas phase. So you have that sort of back and forth that's always sort of happening. This is what is sometimes referred to as Raoult's law. This is PZ is equal to XZ times P naught Z. So this is the vapor pressure of the pure substance is this guy, which is sort of like the solvent. So that's the vapor pressure of our pure substance by itself with nothing dissolved in it. This is sort of the vapor pressure with some stuff dissolved in it of our kind of solution or component. And this is the mole fraction that we just talked about. And that's the mole fraction, obviously, of our component that we're looking at. The vapor pressure lowering may be defined as the vapor pressure of the pure substance minus the vapor pressure of the solution. Because the vapor pressure is going to be lower, we take kind of the original vapor pressure of it by itself minus the vapor pressure of the solution that has stuff dissolved in it. That gives us the change in vapor pressure lowering. That's what the delta stands for there, the change in the vapor pressure lowering. So let's take a look and sort of see how this sort of works here in the problem. So the vapor pressure of ethyl alcohol is 66.5 torr. We want to calculate the vapor pressure of ethyl alcohol in a solution of 0.2 moles of glucose that's dissolved in 1.25 moles of the alcohol. So here we're going to look at Raoult's law. We're going to be looking at the alcohol here. So the ethyl alcohol has a vapor pressure normally of 66.5 torr. We need to figure out the mole fraction here of our alcohol. To figure out the mole fraction of our alcohol, we need to get the total moles like we talked about with mole fraction. So we would add those together. That's going to give us 1.45 moles as our total moles. That means we could take the moles of the alcohol, which is 1.25, and divide it by the total moles to get our mole fraction, which in this case is 0.862, and that would be the mole fraction of our alcohol. Obviously, the 66.5 is the normal sort of vapor pressure of ethyl alcohol. under these conditions. So we now can put it together into that equation and take the mole fraction times the normal vapor pressure, and we end up getting a vapor pressure of the ethyl alcohol that's now dissolved with the glucose of 57.3 torr. What does that mean? It means that the vapor pressure went down. It started at 66.5 in its pure form. Why did it go down? It went down because of what we've been talking about. If we have just ethyl alcohol here by itself, it's going to naturally sort of do this sort of evaporation part, going to create some gas molecules above the liquid, going to create our vapor pressure of 66.5 torr in a normal situation. We now take our same sort of ethyl alcohol, and in addition to the ethyl alcohol, we throw in there some glucose, some sugar basically. I'll just draw the glucose as a square. What's going to happen is, again, the simplest sort of way to think about it is the glucose kind of gets in the way. So it's going to take a little bit longer and a little bit harder for these ethyl alcohol guys to kind of get up and out into sort of the gas phase, which, as you can see in my bad drawing here, we have less gas molecules than we do in the pure guy. Less gas molecules in the pure guy means less gas molecules, less pressure, and that means that we would have a lower vapor pressure in this case, and that's what we see. It actually lowers down to 57.3 torr. Question on that there? Okay, so what we're going to do is we're going to lay it up here for lecture right now.